Hello everyone, this video is brought to you by the Atılım Üniversitesi Open Courseware project. And this is the fourth video section of the video lecture series of Physics 101. The lecture notes are prepared by Associate Professor Dr. Hüseyin Oymak and narrated by Ümit Alkuş. In this video, we will introduce the topic motion in 2 and 3 dimensions. Before I start, let me outline the topics we will cover in this lecture. First of all, we will define the position vector in 3-dimensional space. Then we will continue our discussion by introducing the 3-dimensional displacement vector. Subsequently, we will derive the 3-dimensional average velocity vector. Afterwards, the 3-dimensional instantaneous velocity vector, average acceleration and instantaneous acceleration vectors will be introduced. Next, tangential and radial accelerations will be given. Later, motion with constant acceleration will be discussed. Specifically, we will deal with the 3-dimensional motion. Then 2-dimensional projectile motion. And as an example, we will study the symmetric projectile motion. Finally, we will complete this lecture by working on uniform circular motion. Okay, let's start with position. Recall that in Chapter 2, we denote the position of an object moving along a straight line at any time t according to an origin by x of t. And we had only 2 directions, namely plus and minus. Now consider an object at any time moving in 3-dimensional space like this. Here we have 3 separate 1-dimensional motions, namely the x-axis, y-axis and z-axis. Remember that this is the right-handed rectangular coordinate system. If we specify the origin as this point, the position of the object will be x of t, y of t, and z of t. Finally, by the help of the discussion of vectors in Chapter 3, we denote the position vector of this object at time t by the unit vector notation as vector r of t equals x of t I hat plus y of t j hat plus z of t k hat, which is in meters in SI unit system. For the sake of clarity, we don't write t, and we denote the position vector as vector r equals xi plus yj plus zk. The magnitude of the position vector whose tail is at the origin and whose head is at the point xyz is calculated by applying the Pythagorean theorem twice, as we discussed in Chapter 3. As a result, we obtain the magnitude of vector r as square root of x square plus y square plus z square, and it has the unit meters. In other words, this is nothing but the distance between the origin and the position or location of the object. Okay, let's solve a simple problem. Consider an object whose location is specified according to this right-handed rectangular coordinate system. Then we are asked to find the distance between the origin and the object. To solve this problem, we find carefully the x, y, and z components of this point, which is determined easily as 4, -3, and 4. In the unit vector notation, the position vector r is written as vector r equals 4i minus 3j plus 4k. The magnitude of this vector is nothing but the distance between the origin and the object, and it is found by the formula r equals square root of x square plus y square plus z square, whose unit is unit in this case. Putting the corresponding values into this formula, that is square root of 4 square plus minus 3 square plus 4 square units equals square root of 41 units, and it is approximately 6.40 units. Okay, let's discuss the displacement vector. Consider an object initially at this point, say x1, y1, and z1. And suppose that it moves from this point to another point, say x2, y2, and z2 at a later time. If we denote the position vector of this point by vector r1 and that of this point by vector r2, then the displacement vector, which is denoted by delta r, is found by the subtraction of these two vectors, such that delta r equals vector r2 minus vector r1. In the unit vector notation, it is nothing but x2 minus x1 I plus y2 minus y1 j plus z2 minus z1 k. Alternatively, just as we did in the case of motion along a straight line, we denote displacements in each axis by delta x, delta y, and delta z. Therefore, delta r equals delta x I plus delta y j plus delta z k. Another useful interpretation is this: if the particle's initial position vector is vector r1, and if it undergoes a displacement delta r and arrives at the point whose position vector is vector r2. To illustrate the displacement vector, let's look at an example. Let the object in the preceding example start to move from the initial position vector r1 equals 4i minus 3j plus 4k meter, follows some path, and arrives at the final position vector r2 equals 3i plus 4j plus 3k meter at a later time. Then we are asked to find the displacement vector and the magnitude of this vector. That is, the distance between the initial and final positions of this object. The displacement that the object experiences is delta r equals vector r2 minus vector r1, or in terms of the unit vector notation, x2 minus x1 I plus y2 minus y1 j plus z2 minus z1 k. Putting the corresponding x, y and z values into this equation, we obtain that 3 minus 4 I plus 4 minus 3 j plus 3 minus 4 k. Then we obtain minus I plus 7j minus k meter. The distance between the initial and final positions, that is, the magnitude of the displacement vector, is found to be delta r equals square root of minus 1 square plus 7 square plus minus 1 square meter. That is square root of 51 meter, or approximately 7.14 meter. You should note that this distance is not equal to the length of the path that the object followed. The conclusion, therefore, is that the displacement vector of an object does not give any information about the actual path of the object. It does provide only the net change in the position of the object moving between two definite positions, that is, vector r1 and vector r2. Now, we are ready to discuss average velocity. Consider the object in the preceding examples. Let its position vector at time t1 be r1 and at time t2 r2. Then the time interval is obtained by delta t, and it is equal to t2 minus t1. Like in the discussion of one-dimensional motion, the average velocity vector is defined to be the ratio of the displacement vector to the time interval delta t. That is, V average equals vector r2 minus vector r1 over t2 minus t1. And as you may easily verify, its unit is meter per second. According to this figure, it is recommended to note that delta r and V average are in the same direction. Now let's study an example about average velocity. An object changes its position according to the relation vector r of t equals t plus 1 I plus t squared minus 4 j minus tk, where r is in meters and t is in seconds. Let us find the average velocity between t equals 1 second and t equals 3 seconds. We need first the positions at these times. That is, r of 1 equals 1 plus 1 I plus 1 square minus 4j minus 1k. That is 2i minus 3j minus k meter. And arrow 3 equals 3 plus 1 I plus 3 square minus 4j minus 3k. That is 4i plus 5j minus 3k meter. With this, the desired average velocity is found as V average equals delta r over delta t equals r of 3 minus r of 1 over 3 minus 1 equals 4i plus 5j minus 3k minus 2i minus 3j minus k over 2. Then the result is I plus 4j minus k meter per second. And the magnitude of average velocity is V average equals square root of 1 square plus 4 square plus minus 1 square. That is square root of 18. It is in meter per second. It is approximated as 4.24 meter per second. Well, it is time to discuss instantaneous velocity. Since average velocity is not sufficiently informative, most of the time we are interested in the instantaneous velocity v of an object at some instant. We define v as the limiting value of v average as the time interval delta t approaches 0. That is, vector v equals limit delta t goes 0, the ratio of delta r over delta t. Saying every time instantaneous velocity is somewhat cumbersome. Henceforth, we will say just velocity v without the redundant adjective instantaneous. This definition implies implicitly that the velocity v of a moving object is everywhere tangent to the object's path, as illustrated in this figure. Using the explicit form of the position vector, vector r equals xi hat plus yj hat plus zk hat. This relation for the velocity v leads to v equals dr over dt. That is, d over dt xi plus yj plus zk equals dx over dt I plus dy over dt j plus dz over dt k. Here, it is natural to interpret dx over dt as the magnitude of the velocity vector in the x direction. The similar interpretations follow also for dy over dt and dz over dt. We can thus write the velocity vector in terms of rectangular coordinates in three different forms. V equals Vx plus Vy plus Vz, or Vxi plus Vyj plus Vzk, or dx over dt I plus dy over dt j plus dz over dt k. The magnitude of the velocity vector of an object at a certain time is called its speed at that time. That is, v equals square root of vx square plus vy square plus vz square. Note that speed is always a positive quantity. Now let's solve an example. Let the position of an object be r of t equals t plus 1 I plus t squared minus 4j minus tk, with r being in meters and t in seconds. Determine the general relation for the velocity of this object. Using this, find the object's velocities and speeds at time t equals 1 second and t equals 3 seconds. The general relation for the velocity of this object is determined as v of t equals dr over dt equals d over dt t plus 1 I plus t squared minus 4j minus tk. That is I plus 2tj minus k meter per second. Using this, find the object's velocities and speeds at time t equals 1 second and t equals 3 seconds, such that v of 1 equals I plus 2j minus k meter per second and v of 3 equals I plus 6j minus k meter per second. The corresponding speeds are calculated to be v of 1 equals square root of 1 square plus 2 square plus minus 1 square. That is square root of 6 meter per second and approximately 2.45 meter per second. And v of 3 equals square root of 1 square plus 6 square plus minus 1 square equals square root of 38 meter per second, approximately 6.16 meter per second. In the previous example, we had found the magnitude of the object's average velocity between t equals 1 second and t equals 3 seconds as v average 4.24 meter per second. This result is not equal at all to 1 over 2 of v of 1 plus v of 3, that is 4.31 meter per second, as might have been wrongly guessed. Alright, let's move on to the topic average acceleration. For an object whose velocity at time t1 is v1 and at a later time t2 is v2, we define its average acceleration, which is another vector quantity, as a average equals delta v over delta t equals v2 minus v1 over t2 minus t1, and which is in meter per second square. Now comes the instantaneous acceleration. the instantaneous acceleration a of an object at any time is defined as the limiting value a average as delta t goes 0. That is, a equals limit delta t goes 0 delta v over delta t, or dv over dt. But since v also the time derivative of position vector, that is dr over dt, then acceleration is the second time derivative of position vector, that is d square r over dt square. Since a is a three-dimensional vector, it has components on the x, y, and z directions in the right-handed rectangular coordinate system. That is, a equals ax plus ay plus az. Or, in unit vector notation, it can be written as axi plus ayj plus azk. And since we know from the one-dimensional motion each component, that is one-dimensional acceleration, is nothing but the time derivative of velocity, then we can write a equals dvx over dt I plus dvy over dt j plus dvz over dt k. Since each component is the second time derivative of position, then we can write d square x over dt square I plus d square y over dt square j plus d square z over dt square k. And the magnitude of instantaneous acceleration can be found by the formula a equals square root of ax square plus ay square plus az square, which is in meter per second square. Good. Now we will discuss tangential and radial accelerations. We can decompose the acceleration vector into two components, as in this figure. One of them is parallel or antiparallel to the velocity vector, or tangent to the path of the object, and is called the tangential acceleration at. The other one is perpendicular to v and is referred to as radial or centripetal acceleration ar. The tangential acceleration at is responsible only for the change in the magnitude of the object's velocity, that is, for its speed. The direction of its velocity is governed only by the radial acceleration ar. Mathematically, these two statements amount respectively to at equals dv over dt and radial acceleration ar equals v square over r, where r is the radius of the curvature of the path at the point where the radial acceleration is calculated. The first formula for at here should be obvious from the previous discussion. The second one for ar is subtle for the time being, but will be clear before the end of this chapter. Now it is better to stop here and to solve one example. The position of a bus of old days around the high mountain, which is shown in this figure, could be approximated by r of t equals minus 1 over 10 t cubed plus 2 times t squared minus 10t I plus minus t squared plus 2t plus 12 j. where r is in kilometers and t is in hours. Now we are asked to find the kinematic quantities of the bus at t equals 2 hours. To this end, we first determine velocity and acceleration vectors as v of t equals the r over dt equals minus 3 over 10 t square plus 40 minus 10 I plus minus 2t plus 2j, and the acceleration is dv over dt equals minus 3 over 5t plus 4I minus 2j. The position of the bus in unit vector notation at time t equals 2 hours is r of 2 equals minus 1 over 10 t cubed plus t times t squared minus 10 times 2 I plus minus 2 squared plus 2 times 2 plus 12j, which results in minus 12.8 I plus 12j kilometer. Or we have in magnitude angle notation that r of 2 equals square root of minus 12.8 square plus 12 square, which is approximated as 17.5 kilometer, and the angle alpha equals arctangent of 12 over minus 12.8, which is equal to minus 43.152 degree plus 180 degree, which is equal to 137 degree. We thus say that the bus is at a distance of 70.5 km and makes an angle of 137 degree with respect to the positive x-axis. The position vector r of 2 is shown in this figure. We find bus velocity in unit vector notation at t equals 2 hours as v of 2 equals minus 3 over 10 times 2 squared plus 4 times 2 minus 10 I hat plus minus 2 times 2 plus 2j, which is equal to minus 3.20 I hat minus 2j hat kilometer per hour. The magnitude of v of 2 is calculated to be v of 2 equals square root of minus 3.20 square plus minus 2 square, and which is approximated as 3.77 km per hour. And the angle it makes with respect to the positive x-axis is beta equals arctangent of minus 2 over minus 3.2, which is equal to 32.005 degree plus 180 degree, which is approximately 212 degree. And what about the bus acceleration at t equals 2 hours? We have in unit vector notation a of 2 equals minus 3 over 5 times 2 plus 4 I hat minus 2 j hat equals 2.80 I hat minus 2 j hat kilometer per hour square. Then the magnitude is a of 2 equals square root of 2.80 square plus minus 2 square, which is approximately 3.44 km/h square. And the angle it makes with the positive x-axis is gamma arctangent of minus 2 over 2.80, which is minus 35.5 degree. In this figure, we have decomposed the acceleration vector a of 2 into its tangential and radial components. We note that v and at t equals 2 hours are antiparallel, meaning that the speed v of the bus at this moment is decreasing. We also see that the existence of a fairly large magnitude AR causes the bus to change its direction sharply downward, and as it is clearly illustrated in this figure. We can numerically verify these two observations. The best way to do this is to calculate the speed v and the corresponding angle at t equals 2.1 hours. v of 2.1 equals minus 3 over 10 2.1 squared plus 4 times 2.1 minus 10 I hat plus minus 2 times 2.1 plus 2 j hat, which is equal to minus 2.923 I hat minus 2.20 j hat km/h. And the speed is square root of minus 2.923 squared plus minus 2.20 squared, which is approximately is 2.66 km/h, which is less than v of 2, that is 3.77 km/h, as we claimed. As the angle v of 2.1 makes with the positive x direction, we have b of 2.1 equals arctangent of minus 2.20 over minus 2.923, which is equal to 36.967 degree plus 180 degree, which is approximately 270 degree, which is significantly larger than v of 220 degree, indicating that the bus has turned downward by approximately 5 degree. Very good. This example brings us to the end of the discussions of basic ingredients of three-dimensional motion. From now on, we are going to learn how to analyze a motion with constant acceleration, and we will give some examples of three-dimensional and two-dimensional problems.